Hey, today I'm happy to present our work called Scalable Local Intrinsic Dimension Estimation with Diffusion Models. It involves manifold learning and diffusion models, two of the topics that I'm very excited about. So let's start off with the manifold hypothesis, which at this point in the ML community, it's widely accepted that data used in machine learning lies on low-dimensional submanifolds of their ambient space. What this entails is that for each individual data point, you can assign a value local intrinsic dimension, or LID of X, which is essentially the dimension of the manifold it belongs to. Here we have a kind of like a cartoon illustration that shows both the manifold hypothesis and also kind of forms an intuition of LID, or local intrinsic dimension. These are MNIST digits, and we are depicting two submanifolds, the submanifold of digits 1 and the digits 8. We roughly interpret LID of X as the number of factors of variation. And so if you have more factors of variation, you have more complex data. Here on the left-hand side, we have digits 1 that have a single factor of variation, tilt, and has an intrinsic dimension of 1. Whereas with 8, which we believe intuitively is more complex, we have more factors of variation. Here, for example, we have disproportionality as well. Okay, so we're interested in estimating these LID values, but before talking about that, let me cover some of the applications of this. Actually, recently, yesterday, we presented a poster on using LIDs for doing out-of-distribution detection and explaining a paradox in deep generative models. People have also used LID for detecting AI-generated content and also adversarial examples. The setting that we care about is that we have a diffusion model. It's already pre-trained on a data set, so it has an idea of its manifold, and we want to use that to extract LIDs and then use that for like subsequent applications. Let's take a step back, and I want to interest you in this really cool mathematical result that came out a while back, which links Gaussian convolutions with LIDs. Here we are depicting data distributions supported on a 2D square and a 1D squiggly line on the top and bottom rows. We can define these row of X and delta values. These are the Gaussian convolutions of our original data distribution with Gaussian noise that has log standard deviation delta. And so when we move from right to left, we are convolving it with more and more Gaussian noise. We are increasing delta, and as you can see here, it kind of corresponds to washing off the original density. Now, the cool thing here is that if you see the lower row, the washing off happens much faster. And so intuitively, if you have lower LID, you can wash off the probability density faster. This paper actually rigorously links these two. They have a theorem on stating that when you take the limit of delta to negative infinity, the relation between these Gaussian convolutions and LID in blue here is linear. And capital D is essentially the ambient dimension. So if you somehow have access to these Gaussian convolutions, you can get LID out of it. Before we jump into our work, the paper that originally came up with this theory had a method for estimating LID. What they did is that they took the data set, they augmented it with various levels of Gaussian noise. So they have M different data sets, and they train M different normalizing flows on each data set to estimate these Gaussian convolutions. And they use a linear regression to get the LID out of it. At a first glance, it seems kind of wasteful because you're augmenting the data and you're training multiple normalizing flows. And also, we know that normalizing flows aren't the best generative model, especially in these scenarios where the intrinsic dimension is lower. So obviously, we use diffusion models, but not just because they're better, but actually this process of Gaussian convolution has a striking resemblance with what happens in the noising process of a diffusion model. And so we have our method called Fokker-Planck LID. We use the Fokker-Planck equation of a diffusion of the stochastic differential equation of a diffusion model to get an LID estimator. To establish some notation, diffusion models are defined using a forward SDE, stochastic differential equation, that's denoted using the functions f and g, the drift function and the diffusion coefficient. All of the diffusion models that we care about in practice, DDPMs, variance exploding, everything, they have a Gaussian transition kernel, which is parameterized using psi and sigma squared. Everything that's color-coded in blue, you can analytically compute it based on the diffusion model that you've chosen. Score-based diffusion models, they're essentially they're UNets. They learn a score, which is the gradient of the log marginal probability. And what we do is that we link these marginal probabilities with these Gaussian convolutions in a rigorous manner. What we do is that we theoretically show that as delta goes to negative infinity, instead of doing a linear regression as opposed to the previous method, you can actually take the derivative of these log Gaussian convolutions, and that will give you, with respect to the log standard deviation, and that will give you the LID. So we replace that log standard deviation with a term that's denoted here. The only thing that's important here is that now instead of Gaussian convolutions, we have the log marginal probability. And so if we expand this formula and look at it, we can apply a chain rule on the left-hand side and write the derivative in terms of time instead of the standard deviation, and then we can get a and then there is where the Fokker-Planck equation pops up. So I'm not going to go into the math more than this, but we essentially come up with a single formula that can estimate LID efficiently. So on the left-hand side here, you can see LID hat of x and delta. It depends on a hyperparameter delta. In theory, you have to send delta to negative infinity so that it is actually equal to LID. But in practice, we just set it to a small value. The formula might seem a little bit intimidating in the beginning, but this is the most general case of the formula. So everything that's color-coded in blue, based on what you choose, DDPMs, variance exploding diffusions, you can analytically compute it using a closed-form formula. Now, there are two terms here that are of interest. On the right-hand side, we have an L2 of the score, which you can compute using essentially a forward pass of the diffusion. And then we also have a trace of the Jacobian of the score, which pops up a lot in the diffusion literature. People use the Hutchinson trace estimator, and they do a few JVPs instead of computing the whole trace, and they get unbiased estimators for it. So this is our formula. It's a one-liner formula, and you can get LIDs out of it. You sat through the math with me. Let me show you some pictures. We applied it on Lion aesthetics images that are of 1 million dimension. This is the first time we're able to estimate LID on such large-scale data. And we actually use a single JVP to estimate the LIDs here. When we look at the highest and lowest 8 LIDs, we can see a clear split in terms of the complexity of the data. We also see the same thing across a lot of image data sets. The top half are much simpler. The bottom half are much more complex. They have more textures and details. We also extensively benchmark our method across a lot of synthetic manifolds, where we generate complex manifolds that we have access to the ground truth LID. We compare it against a lot of methods. Our method is not only fast, but it also obtains state-of-the-art results across all of the benchmarks. So to summarize, our LID estimator, it qualitatively extracts data complexity with a pre-trained diffusion. One thing I didn't mention is that we found a striking correlation between our LID measures and PNG compression rate. So this is really exciting because you can think of this as a continuous proxy for PNG compression rate. It is theoretically grounded. It achieves state-of-the-art. And it is the first one that can scale to images of such high dimension. And most importantly, it's differentiable by design, so you can think of all the endless possibilities you can do with it in deep learning. Thank you. You can also scan these QR codes. We have a website on our work. Thank you so much.